Hello everybody, welcome to the second lecture in the foundation series for physics. My name is Dr. Naveen Rawat and this lecture is going to be about a review on vectors. So let's begin with reading a little bit about what a scalar is. And a scalar is any quantity which is invariant under a coordinate transformation. If we talk in simplistic terms, basically what it means is any quantity that can be described just by one number and a physical unit is actually a scalar. For example, mass, temperature, speed, these are all scalar quantities. And you might be familiar with the definition that you have read in school is that a scalar quantity is any quantity in physics, for example, that has magnitude only. And it is represented by some number value and appropriate units to go along with it, right? So for example, speed, if we have to designate what speed is, it is 35 meters per second could be a value of the speed. Similarly, if we are trying to find age of a person, we can write it as 16 years. So these are examples of what a scalar is. What we are interested in during this talk is about vectors, and essentially a vector is a quantity that has both size and direction. For example, wind, your forces in physics, these are examples of vector quantity. And geometrically, it is denoted by a line segment where you have a tail that is the initial point, and the head, which is given by this arrow, and that points to your terminal point. And this is how a vector is represented. Okay. And you might be familiar with the definition that you've read in school, which is that a vector quantity is any quantity that has both magnitude and direction. For example, if we talk about velocity, uh, it can be written as 35 meters per second, and the direction of the velocity is north. So we have to specify both the magnitude and the direction for these quantities. And there are other examples like acceleration, displacement, force, and these are all examples of vector quantity. So let's look at a simple example. We have a case in which a person is walking 46.5 meters east, and then he walks another 20 meters east. So if you want to find the total displacement relative to where he started, we have a situation that can be represented by this vector addition. Okay, and the final answer that we get is 66.5 meter. That is the displacement, and the direction will still remain east. So this is one way to add the vectors. Similarly, if you have vectors that point in opposite direction, you can go ahead and simply subtract them. This methodology of putting the tail of one vector to the head of the other is a very useful method known as the graphical method. And suppose you have to add not just one or two but many vectors, you can do and find the resultant vector by just drawing the vector from the initial point to the final point of this vector. Okay. You might also encounter a case where you have collinear and non-collinear vectors. So, for example, let's take this first case where you have two vectors. These are forces that are acting on this object, and these forces are acting along the same line in the opposite direction. So let's assume that the magnitude of these forces is the same, and if in this scenario you will see that because these forces are along the same line, they will cancel each other out and there should be no motion. However, you might have a situation in which the forces are not collinear. Okay, and in most of these cases, what you can do is you can apply the Pythagorean theorem. So let's look at an example. A man is traveling 120 kilometers east, and then he travels 160 kilometers north. So it is represented in vector notation as shown here. So this is the start point, and you have one vector that points in the east direction of magnitude 120 kilometers, and then another vector that points in the north direction and has the magnitude of 160 kilometers. So you can use this tail to the head technique, and you can find the resultant vector c by using the Pythagorean theorem. So according to the Pythagorean theorem, the square of this hypotenuse will be equal to the sum of the squares of these individual vectors a square and b square. So if you do that, we get a resultant value of 200 kilometers. So we haven't said anything about the direction of this vector. And to record the direction, generally you can use the north, south, east, west scale as represented in this figure here. So in our particular case, when the displacement is happening to the east and then to the north, the final position we can represent as north of east. To be much more quantitative, what we can do is we can define an angle, and this angle theta, again by using trigonometry we can find, from trigonometry we know tan theta is opposite side by adjacent side. So you have this 160 kilometers by 120 kilometers, and this helps you find the exact angle from the origin in which direction the resultant vector is pointing. Okay, so then the complete final answer can be represented like this. You have the magnitude 200 kilometers and 53.1 degrees angle north of east is where the final position is. There is a very common vector notation that is used with angle brackets that you might not be familiar with, and essentially this notation is saying that this vector is having a position of A on your x axis and a position of B on your y axis. So essentially it is telling you that from an initial point 0 0 where your terminal point is lying, and the terminal point is A comma B, and when we represent it as a vector, it is given by this angle brackets right here. Suppose you have a vector that is represented by a certain uh, length and direction, and if you have another vector that is of the same length, although it is displaced on the axis, since it has the same length and same direction, then these two vectors are essentially equivalent to each other. Okay, and there are other operations that one can perform on these vectors. Suppose you have a vector v that is represented as a comma b, and there is another vector w that is represented as this angle bracket c comma d. Then if you want to add these two vectors, so all you have to do is you have to add these components. So if you add v plus w, the resultant will be a plus c comma b plus d. Okay, similarly if you want to find a magnitude of a vector, then from this notation the magnitude of the vector will be square root of the first component square a square plus the second component square b square. Okay, and so right now we are talking about only two dimensions, but as you might be aware that when you go to a three-dimensional case, your notation can change from a b to a comma b comma c, because now we will be considering the three dimensions of your uh, axis, and in each dimension these a b c they represent the magnitude of the vector in that particular direction. The scalar multiplication is a common operation that vectors undergo through, in which basically you are multiplying the vector with a scalar, and if you do that then you have to multiply each and every individual component of the vector with the same number. Okay, so if you have a four dimension or a five dimensional axis, then all the five dimensions you will have to multiply this number with the each and every component in that dimension. Okay, so another methodology to add the vector is by using the parallelogram method. So we have two vectors here, vector a and vector b, and we want to find the resultant vector by adding them. And so all we have to do is we have to combine the tail of the one vector to the tail of the other, and then basically we have to form a parallelogram in this format. And once you do that, the diagonal of the parallelogram gives you the resultant vector. So you might have a vector that is of negative sign pointing in the opposite direction, and then you can apply the same method. You can draw a parallelogram, and then the resultant vector that you will get will be pointing in another direction like shown here. Okay, so this is your resultant vector, which will be a minus b. So let's do some examples. Suppose you have a given vector a of the format 4 comma minus 7, and if you are trying to find the magnitude in this case, then like I mentioned before, the magnitude of a will be the square of all the components of this vector. and so you will get a square root of 4 square plus plus minus 7 square. So you will get the magnitude A is equal to square root of 4 square, which is 16, plus minus 7 square, which is 49. So the total magnitude of this vector is square root of 65. Okay, and you can go ahead and practice some other examples as well. So the important concept that we want to talk about next is the concept of unit vectors. You will be definitely encountering this in higher level mathematics and physics. And essentially, a unit vector is a vector whose magnitude is 1. So it is a very convenient quantity to work with. And typically, the way we represent these unit vectors is by using symbols like I and j. So this I is a unit vector that is pointing along this x direction as shown here, and this j is a unit vector that is pointing along the y direction as shown here on the xy axis. Okay, so if we use the notation that we are using so far, this I vector uh, will be given as this angle bracket 1 comma 0, and the j vector will be given as 0 comma 1. Okay, so in many textbooks you might see a hat put on top of this vector to represent it as a unit vector. You might also see a case of people using x cap and y cap or italic format. So different notations might be used, but essentially they mean the same thing, that if you have a vector v that is represented as 3 comma 5, you can represent this in terms of this unit vector scale, which is 3i plus 5 of j. And this, as you will see, it will help us do a lot of mathematics and calculations very fast. So let's start doing some examples. Suppose you are adding two vectors. The first vector is given as 4 comma minus 4, and the second vector is given as 6 comma 9, and we want to add them. So basically this first vector can be represented in I and j format like this: 4i minus 4j, and the second vector will be 6i plus 9j, and when you add them, you will get 4 plus 6 will be 10 times I, and minus 4 plus 9 will be plus 5. So you get 10i plus 5j. So you eventually you can write this vector as 10 comma 5. Similarly, if you want to find the magnitude, you can ignore this I values and just take the square root of these numbers, and so the magnitude will come out to be 5. Similarly, if you want to find the direction of a particular vector, like I had shown before, you can use the trigonometry and write the value in terms of tan theta, and from here you can take the inverse and find the theta value. Okay, so it is generally useful to represent a circle with radius 1 and use it to depict these vectors. And as you will see, so you have this cos of this angle value here, and by definition cos of along this line, the angle is 0, so the maximum value possible is 1. Similarly, along the y-axis you have a sine of the angle value, and this angle value sine maximum value when it is 90 degree, which then the vector is pointing in this direction, and the value will be 1. So a unit circle is a very common thing that is used to describe which direction the vector is pointing in. Okay, similarly, a common process that we do to solve a lot of problem is actually decomposition of a resultant vector. And you might have done this while solving electric fields or resolution of forces, where if you have a vector v that is represented like this, you can decompose it into your coordinates of a and b along the x and the y axis, and essentially this value of a is nothing but v times cos of this angle, because we know that the cos of the angle is adjacent side by hypotenuse. And similarly, if you take sine of the angle, the sine of the angle is opposite side by hypotenuse, so you get the value for b as v times sine theta. And so if you just know the direction and magnitude of a vector, you can decompose it into its components on the x and y axis. So the first product that we will be talking about is the scalar or dot product. And essentially in this product, what is happening is that you have multiplication of two vectors v and w, And when we multiply these two vectors in the dot format, basically what we are doing is we are taking the projection of this w vector on this v vector, and then multiplying that value to the value of the v vector. Okay, so mathematically it is given by a dot uh, product like this, v dot w, which will be equal to the magnitude of the v vector and the magnitude of w vector times the cosine of the angle between the two vectors. So this w cos alpha is what is the projection of your w vector on the other vector to which it is getting multiplied. Okay, so from this formula you can again, if you know the vectors and you know the magnitude, then you can find the angle between two vectors as well. Okay, so there are some very common properties of the dot product, that they are commutative, they are distributive over the addition, and so we can take a dot product of a vector with itself, and if you multiply it with 0, then you will get 0. And essentially there are some notations that you should be familiar with, that if you are taking a dot product of I unit vector with I, then the value will be 1. And if you take a dot product of I with any other axis, let's say j or k, then the value will be 0. And the reason why this happens is, if you remember your three-dimensional axis, the I, j, and k are all uh, pointing at an angle of 90 degree to each other. So you have your three-dimensional axis, and I is along the x-axis, and you have the j unit vector along the y-axis, and you have the k unit vector along the z-axis. So the angle between them is 90 degree, and so every time the angle is 90 degrees, you have a cos of 90, which gives you 0. So the dot product of I with j and j with k, and similarly k with I, will give you value of 0. However, when you do I dot I, the angle is basically 0 between these two vectors, so you will get a result in terms of 1. So let's do an example. Here you are given three vectors a, b, and c, and we want to take the dot product. So when you take the dot product of vector a and vector b, essentially, like we were saying, I and I can get multiplied and form 1. So the first term will be 3 times minus 2, which is the multiplication of these two values, and the second term uh, will be the multiplication of your j dot j, which will again give you 1, and so you get 7 times 4, and the other terms, which are the cross multiplication of I dot j, which are these terms right here. So you have I times this number here, and that will be 0, and then you have j dot I, and this will also result in 0, right? So it doesn't matter what components they have in front of them, but the resultant value will be 0. Okay, so then a dot b will simply be minus 6 plus 7 fours are 28, and so you get a resultant of 22. Okay, so again, it's called a scalar product because you're just getting a number value at the end. Okay, similarly you can perform the exercise for b dot c and calculate what it is. The reason why we are interested in dot product is because it appears in physics most of the time, because you might be familiar with work done, which is a very important quantity that we try to calculate in physics. And essentially the work done formula is a dot product between force and s, which is the displacement. So the complete formula for work done is your magnitude of force times the magnitude of s, which is the displacement, times the cos of the angle between the force and the direction of displacement. So for example, you have a horse here pulling a cart and a man, and the angle between this displacement along the snow and from application of force is 37 degrees. So your work done will be your f value, the magnitude of f, and times the magnitude of s, times the cosine of the angle between them, which is 37 degrees. Okay, so from here you can realize that the maximum work done will be when this cos value entire term will be 1, and so the alpha has to be 0, so along the same line of the displacement. Okay, so similarly there are other terms in physics like power, where you again have to use the dot product. There is another type of product that is very common, that is used in physics, and it is known as vector product. Okay, and the way vector product is represented is very different. It is written as a cross b. So a cross b is the vector product of a and b, and we can represent it as vector c. And mathematically this value of c will be magnitude of a times magnitude of b times the sine of the angle between these two vectors. Okay, so let's take an example. Here you have two vectors a and b, and they form an angle between them which is theta. And what we want to do is we want to use the right handed coordinate system. This is very important. So you have to use a right handed coordinate system, and you have to curl your fingers when they're pointing in the a direction towards b, and once you do that, you will see that your thumb will point towards the c direction. Okay, so any two vectors represented here like a and b, they will form a plane, and this resultant vector c, which is a cross product of a and b, will be perpendicular to this plane that is formed from a and b vector, and the direction will be given by the right handed coordinate system. What we mean is, if let's say this is the x direction, and the next direction that we get when you go counterclockwise will be your y axis, and the next axis that you go counterclockwise will be your z axis. Okay, so by definition, this progression of x to y to z is what we are saying is the right handed coordinate system. And if you go clockwise, that would not be the right handed coordinate system. So to do the vector product, you have to always remember that it's better to just follow the right handed coordinate system, and that will give you the right direction of your vector. Okay, so mathematically, to calculate this value, it is useful to write it in matrix notation. So suppose you have two vectors a and b, and they have their components a1, a2, a3, and b1, b2, b3. So we can write it in matrix form in such a manner. You first row you can write it as the components I, j, k, the unit vectors pointing in the particular directions, and then the next line you can write as the components of the vector a, which is a1, a2, a3, and the next one row will be the value for the components of the b vector. Okay, so to do the entire product, what you need to do is you need to take this I unit vector, and then multiply it with the determinant by eliminating this row. So you have I, and then you are multiplying it with a2, a3, b2, b3 sub matrix right here. Okay, similarly with j, you have to put a negative sign in the middle one, and then you eliminate this row, and you have a1, a3, b1, b3 as your matrix that you need to calculate the determinant for. And with k, you will eliminate the row beneath the k1, and you will have a1, a2, b1, b2, for which you have to find the determinant. Okay, and determinant is just you can just take the cross multiplication here. So the first term will be a2 times b3 minus a3 times b2. Similarly, the next term here will be a1 b3 minus a3 b1, and the k term will be a1 b2 minus a2 b1, and so you get this entire expression, which is the cross product of a and b. Okay, so there are a lot of vector properties that you need to be aware of. For example, a cross b is not the same as b cross a. Remember, we were talking about the right handed coordinate system here, right? So x cross y will be z, but y cross x will be minus of z. Okay, so you have to be careful about that. Okay, and we won't go into detail of solving these. You probably have done it before in class, but you need to remember these. And the most important uh, condition that you need to remember is this orthogonality condition of the unit vectors, in which if you have the unit vectors, by definition of our right handed coordinate system, they are at 90 degree to each other. So if you take I cross j, then you know that the resultant vector is pointing in the k direction. And similarly, if you take k cross I, you know that it is pointing in the j direction, and so forth. Okay, so again, right handed coordinate system is very important. So one of the applications that we apply the cross product is to calculate the force on a charged particle when it is moving through a magnetic field. So for example, here you have a charged particle that is going through the a magnetic field, and essentially this magnetic field is represented as this dots. That means the magnetic field is coming out of this screen, and whenever there is a cross mentioned, that means the magnetic field is going inside the screen. Okay, so that is just by notation of a vector. Okay, so now you have a charged particle that is going along this direction, represented by the velocity v, and there is a magnetic field that is perpendicular to it. So then the force acting on this particle will be the cross product of this value, which is the charge q v, which is a vector, cross b. Okay, so the resultant value mathematically will be q times the magnitude of v times magnitude of b times sine of theta. Okay, so as you can see in this case, because of the application of your magnetic field and the motion of charge along a direction which is perpendicular to the b field, so the resultant force that develops is towards the top of this screen. And so the charge will not follow a straight line, but it will follow a kind of circular orbit. Okay, again, from the animation that is shown here, you can see that the maximum force that will develop on this charged particle is when this vector v is perpendicular to the vector b, and that you can see from this formula as well, because when these two are perpendicular, then the sign value will be 1, which is the maximum, and that gives you the maximum force. So thank you very much for your attention, and I hope this review was useful for you.